So if we don't have a graph to evaluate a limit, then we're going to use an equation. Now, one of the ways that you can use an equation is a table. Not really an ideal way to do this. We're going to talk about lots of other methods, but the table method really helps understand the concept of limits from the left and limits from the right. So we're specifically asked to use the table method to evaluate the following limit. I have the answer off to the side, and it really should have f of x or the function notation written here, but we're going to find out the limit is 4. So if we were just going to plug 2, the limit we're looking for x's value to be, into the function, you'll notice that we're going to end up with 0 divided by 0, which does not exist. You may know L'Hopital's rule and indeterminate values, but at this point we're only using the knowledge provided so far. So we need to consider a table. So I want to look at the limit going to 2 from the left. So I need a number smaller than 2. For example, 1. I'm going to plug 1 into the function, and I'm going to get 3 out as the function's value. But I should be closer to 2. So if I used 1.9, still to the left of 2, and that little bit closer value gives me 3.9. 1.99 is even closer to 2 from the left-hand side to give me 3.99. If I want a number that's bigger than 2, a number on the right side, so 2 plus, I could have picked 3. When I plug a 3 in for the function, I get 5 out. But I should be closer. 2.1 is on the right side of 2, but closer to give me 4.1, and all of this math is off to the right side. 2.01 is even closer to 2, but still on the right side, and it gives me 4. So as I'm just looking at numbers on the left side of 2, 3, 3.9, 3.99, it's getting really close to 4. Numbers that were bigger than 2 had outputs of 5, 4.1, 4.01, they're getting closer to 4. These numbers match to give me a limit of 4, and that's the table process. Now, one other thing that this leads to is considered instantaneous velocity. So we'll talk about velocity in a second, but instantaneous specifically means at a single point in time, just at x equals 2. Not 2 from the left, not 2 from the right, kind of conceptually, but just 2 itself. So if you were to take velocity and take the average of velocity, y2 minus y1 over x2 minus x1, but in our case, we may be using a function of s for distance and t for time. We want to look at the change in the position divided by the change in time to get average. The problem is, change in time is 0 if it's instantaneous. What is the change from this second to itself? There is no change to itself. So we would therefore be taking some change in position and dividing by 0. So we would say the average velocity does not exist, but that's not true. We can use limits to find the average velocity. So in this case, we'll use tables to emphasize the skill just taught. The problem reads, thanks to Galileo, we know that the distance that a dropped object travels is given by s of t equals 4.9 t squared meters. So this is always true. Distance in meters is based on t, time as an input. We're asked how fast, not the distance, that the object is falling after 3 seconds. So we're actually looking for average velocity, and I need to take the limit of this function as t approaches 3. So I need to look at 3 from the left side, which something smaller than 3 would be 2.9, or 2.99 is even closer. The math is off to the side. It might be hard to determine going from 28.91 to 29.351 that we're headed towards this value. But if we looked at numbers bigger than 3, such as 3.1 to get an output, or closer but yet still bigger, 3.01, we're really kind of looking where do these numbers hit. And this first one rounds to 29.4. This rounds to 29.4. So we're going to go ahead and use the average velocity is 29.4. The important information for topics coming up is that what we found is the tangent line at 3 seconds, and specifically 29.4 is the slope of that tangent line.